DC motors are motors that utilize the motor effect to spin an axle, converting electric energy into mechanical. They are used in many electric devices that require a spun part, including the fans and hairdryers, the motor inside electric drills, and, by attaching an offset weight to the axle, can be used as a vibrator for phones and other devices. The motor effect is an electromagnetic effect in which a current running perpendicular to a field produces a force perpendicular to both the magnetic field and the current. In three dimensions, if the x-axis is current and y is magnetic field, the z-axis would be the force provided by the motor effect. In a DC motor, wire is wrapped around poles on the armature as a coil, increasing surface area and therefore current according to Ampere's law. The part of a coil running parallel to the axis provides a force up and down on either respective end, creating torque until the wire is parallel to the magnetic field, reducing the torque to zero as the force is now in line with the armature poles. At this point, inertia carries the armature around slightly further, in which the split ring commutator physically reverses the current by making contact with the opposite brush. This process is repeated, accelerating the motor until friction limits the speed. A standard brushed DC motor has these parts: split ring commutator, electrical contact point attached to the axle, which physically reverses polarity upon rotation. It converts the direct current into alternating current. Brush, electrical contact to the commutator, transfers current to armature. Coil, wire wrapped around an electrical pole, increasing surface area to magnetic field, thus increasing current. Magnets provide magnetic field, applying constant attraction and repulsion to armature. The armature carries alternating current provided by the commutator. It is the physical support for the coil. Motors also consist of the stator and the rotor. While most modern DC motors use more than two poles, the concept behind them is the same, and the entire process can be summarized in 4 steps. Current is applied to armature, pushing the poles upwards and downwards. Armature pole reaches parallel with the magnetic field, where inertia carries it slightly further. The commutator reverses the electric charge, and thus the force due to the motor effect. The down becomes up. The armature continues rotating to the other pole, where step 2 is repeated. I created my motor out of Lego pieces and copper to carry the current. I used rare earth magnets to provide the magnetic field. Initially, the magnet's attraction was so strong I had to add a support to prevent them from breaking free of the Lego constraints. I also initially tried using a 9-volt battery for the power source, but moved up to a remote-controlled car battery to increase the current, and as the 9-volt had been drained. To apply the current, I fashioned these copper brushes using basic plates and alligator clips. As a commutator, I used more copper plating and glued it to a circular Lego piece. I coiled wire around this pole design, soldering it to the commutator. All in all, the motor works like this. Before filming, the motor was able to get really fast. The wires attached to the alligator clips are very thin, however, and quickly heated up and stopped working properly. While the motor still spins, it is very limited in how it does so. The commutator is also not perfectly circular, meaning the brushes get caught on it often, causing high friction, slowing the motor down. Doing this again, I would make sure to have a more circular commutator and better brush wires.